Today we're going to talk about NP-completeness reductions. It's a really cool topic. I hope you think so too. And please feel free to stop me at any time along the way with this if you have any questions, if anything's not clear. All right, so Ryan tells me that you guys already know some things. You guys already know that 4 coloring reduces to 3 coloring. Have you guys seen this before? And this is what's called a polynomial time mapping reduction. You guys have looked at that already? All right, cool. So I can write it like this and not, technically I'm supposed to write it like, and this is, a poly time, this chalk's not so good. Mapping reduction. So that's what it technically is, but I'm just going to write this because it's just kind of quicker. So yeah, so you know the 4 coloring reduces to 3 coloring. You also know that SAT reduces to 4 coloring, yes? All right. You also know that circuit SAT reduces to SAT, and that 3 SAT reduces to circuit SAT. All this familiar? Okay, cool. There's some other things that you learned. So last time, I guess you talked to you guys about this Cook-Levin theorem. It's an amazing thing where they showed that circuit SAT is actually NP hard. Well, actually, it's NP-complete, and so intuitively, NP-complete means that circuit SAT is at least as hard as any other problem in NP. And technically, there's kind of 2 parts to showing that something is NP-complete. Any of you guys remember what those 2 things are? Exactly. So, so that means it's a particular circuit SAT. Sorry, this chalk I'm not doing so well with. I don't know what's going on with that. Let's see if I can find anything else. So yeah, circuit SAT is in NP. And 2, circuit SAT is NP hard, which means that essentially all problems in NP reduce to circuit SAT. So yeah, there's these 2 things. So 1, the problem has to be in NP. 2, all problems in NP reduce to circuit SAT, i.e. circuit SAT is NP hard, exactly as you said. And this means the circuit SAT is NP complete. So this is what Cook-Levin showed. Okay, so also, because we have these reductions, we also know that, there we go, that the fact that circuit SAT is NP complete means that 3 SAT is also NP complete. So this is kind of what you should already know, what you should already kind of be familiar with. You guys have any questions about that? All right, now today, what are we going to do today? Today, we're going to show a few things. We're going to show that 3 coloring rather reduces to 3 SAT. So that kind of makes this now kind of a cycle. of reductions. And in particular, this means that kind of all 5 of these problems are going to be NP-complete. And so what we're saying is we have all these problems, and they're somehow equivalent in the sense that if you can solve one, you can solve all the other ones. And furthermore, there's actually kind of thousands of natural problems that are also NP-complete, and if you can either solve the Mellon polynomial time, you can solve, or if p is not equal to NP, which we believe to be true, you can't solve any of them in polynomial time. So that's what we're going to show this first, and steps there to showing that are going to be first to show that 3-SAT is this problem called E3-SAT reduces to 3-SAT, where this is has exactly 3 literals per clause. Then we're going to show that NAE-3-SAT not all equal 3-SAT, which I'll define that more when we get there. Reduces to 3-SAT, and then we'll show that 3-coloring reduces to NAE-3-SAT. So that's how that's going to go. And then, so this is kind of the first thing. The second thing that we'll hopefully be able to show is that this problem called independent set. Have you guys seen independent set? Have you guys heard of independent set? I'll tell you guys about it when we get there. An independent set also reduces to 3-coloring. And the interesting thing there is that up to this point we'd really been talking all about CSPs. And so you guys saw what CSPs were on your homework, from what I heard. Yeah, so all these things like coloring and SAT and NAE-3-SAT that we're going to talk about, they're all CSPs. So they're all constraint satisfaction problems. Independent set is not. So we're going to see an example of a reduction showing that a problem that is not a CSP is also NP-hard and therefore NP-complete. Okay, so that's kind of the overall outline for today's lecture. You guys on board with this? You pumped? It's 9 in the morning. It's kind of tough to be pumped at 9 in the morning. All right. So before we get into that, let's just again recall how we show NP-completeness. So first, we're going to show, where we have some decision problem L, and we're going to show, I should write that down. So we're given a decision problem L. So one, we want to show that L is in NP. Typically, this is easy. It's usually kind of self-evident. For this lecture, I'm probably just going to maybe say this out loud and say, yes, notice this problem is in NP. Usually a straightforward thing. And two, we're going to pick an NP-hard decision problem S. For example, often we choose 3-SAT. And we're going to show that L reduces to S. And so to do this, to do this is to use a reduction. And a reduction is an algorithm. It's just an algorithm. So somehow, even though we're doing complexity theory here, we're just giving an algorithm that takes an instance of this problem S to an instance of L such that we want to accept this if and only if we accept this. And so even though we're doing complexity, we're doing an algorithm. And so Ryan wants to point out that this is kind of one of the themes he wanted to show, is that a lot of complexity theory is really about algorithms. And this is one example of that. All right, so we're going to be doing this a lot today. And we're kind of showing this for these particular problems. But kind of as you kind of go on with your life, you'll be doing maybe computer science somewhere or something. And it can be nice to kind of have a sense for how these reductions go, how these problems look, so that when you run into a problem that you've never seen before, you can say, maybe this is actually NP hard, and I should not expect to do it quickly. So maybe a small practical benefit there. All right. So let's start with this E3-SAT problem. So we're going to start with step one of our. So we're going to start with, we want to show that 3 coloring reduces to, 3 coloring reduces to, I keep saying this backwards. 3-SAT reduces to 3 coloring. There we go. And we're going to start with this first step. So we have this E3-SAT problem. And that is just the same as 3-SAT, except we have that every clause has exactly 3 distinct literals and 3 distinct variables. Guys, is definition clear? All right. So a couple remarks here. One is this distinction between E3-SAT and 3-SAT is largely for technical reasons, for our convenience as we do these reductions. You should not think of this as being a significant distinction conceptually. So really, just kind of by requiring every clause of exactly 2 variables, you'll see later this kind of makes this a reduction that we're going to use to show ours to 3 coloring. That'll make that go easily. But we're just being careful about this just because we want to do it right. We want to do it technically correctly, but not a conceptually important thing. That's remark 1. Remark 2, and I'm just going to say this in words, E3-SAT is in NP, of course. 3-SAT is in NP. E3-SAT is a special case of that. So we did part 1. Great. All right. So what are we left with? Well, we're left to show the following proposition. Okay, and we would, of course, like to prove this. So how do we want to prove this? Well, what we would really like is a polytime algorithm that's going to take a 3CNF phi to a 3CNF phi prime such that each clause has exactly 3 literals. And of course, we'd like it to be the case that phi is satisfiable if and only if phi prime is satisfiable. So this is kind of this is what we need to do to do this proof. Can you guys read my writing? Okay, good. Let me know if you can't. Okay, so of course, if we're looking through our clauses of phi and we have exactly exactly 3 literals, they're all distinct. That's great. We don't need to do anything. But what problems can arise? So there are kind of 2 problems that can arise. So one is that a clause contains both a variable and its negation. So we wanted 3 distinct variables as well. Can anyone tell me why this is not a big deal? What do you know if a clause contains both a variable and its negation? Yeah, I think I saw your hand first. Yeah, the clause has to be true. So then you might as well just throw it out because it doesn't affect satisfiability of your formula at all. Okay, yeah, so this is always satisfied. So we may as well just delete it. So this is not a big deal. What is a big deal? What is a big deal is that a clause may have only 1 or 2 literals. Or equivalently, a repeated literal. So this is really the case we have to deal with. Okay, so how are we going to do that? So here's an idea. What we would really like to do is something like this. So say, we have this clause x6 or not x9, and maybe we'd like to somehow turn it into something like x6 or not x9 or false, like that. And so now we somehow have 3 things in our clause, and we can satisfy this one if and only if we can satisfy this one. Because the false means we need to make one of these true, at least one of these true, which is the same thing as satisfying this. But we can't just throw in false and true in there. We actually need to throw in a real literal. So what we kind of want to do is to have a variable that's always false. All right. Does this idea make sense? So if we had a variable that was always false, we could throw it in here, and we'd get this nice thing where you could satisfy this one if and only if you can satisfy this one. Okay. So how are we going to do this? Well, it's pretty straightforward. So now we'll kind of get into the actual details of this. So we're going to get this phi prime, we're going to add to phi some stuff. So what are we going to do? So we're going to, or rather, maybe it's clearer to think of this as being constructing phi prime from scratch. Let's think about it that way instead. So we're constructing phi prime from scratch, and so we're adding these things to phi prime. And so what are we going to do? We're going to add variables A, B, C, new variables A, B, and C. And then we're going to add some clauses. And we're going to add clauses not A or B or C, A or not B or C, A or B or not C. Or in fact, we're going to add all 7 clauses with the exception of not A or not B or, no, sorry, all 7 clauses except for A, B, or C. So it's going to look like, we'll continue in the same way. Let's see where I'm at. Oh, 2 more. then the last one is not A or not B or not C. Great. Okay. So if I have these 7 clauses, what do I know about A, B, and C that satisfy these clauses? So again, these are all clauses except for A or B or C. They're all false. That's exactly right. So that means that any assignment satisfying phi prime must have A equals B equals C equals false. And for example, just to kind of make this completely clear, say that you had A is false and B is true and C is false, then this is ruled out by the clause A or not B or C. All right, cool. Yeah, does it make sense? So everything's false. All A, B, and C are false, rather. Then we're in great shape because this is exactly what we wanted to do, right? We wanted these kind of extra false variables we could throw in for these slots, in these clauses so that we get 3 variables per clause. And so this is what we're able to do. Okay, so we can, I guess, state this on the board. So we're going to say that for each clause of phi, if we have 3 literals, just add it to phi prime. If 2 literals, we're going to add A to the clause, and then add the clause to phi prime. So this is like our example above, where I have x6 or not x9, and I instead make this x6 or not x9 or A. Then, if 1 literal, we're just going to add A and B to the clause in the same way. And then we're going to add the clause to phi prime. And that's the reduction. Does this make sense? All right, so we constructed these false variables by adding these 7 clauses. We're just using these to fill out the clauses that don't have 3 distinct literals already. And so maybe we should note that if phi has m clauses, phi prime has m plus 7 clauses. So that's, everything is polynomial size. Everything can be done in polynomial time. It's all very nice. All right, cool. So now what do we need to do? We should probably show that phi prime is satisfiable if and only if phi is satisfiable. All right, so where should we do this? Let's do this over here. Phi is satisfiable if and only if phi prime is satisfiable. So there's two directions here. In this direction, we're going to say, so in this direction, I mean, we're going to assume that phi is satisfiable and then show that phi prime is satisfiable. So we're going to say that we have x that satisfies phi, then phi prime is satisfied by x, a equals false, b equals false, c equals false. And yeah, and that's clear from the reduction. And the other direction is sort of equally clear. And so there we're going to say that phi prime is satisfied by x, a, b, c. Then we know that a equals b equals c equals false. And so it must be the case that x also satisfies phi prime. All right, so we've shown that 3-SAT reduces to E3-SAT. Make sense? Any questions about this before we move on? All right, and like I said, this is kind of a warm-up. We're kind of doing it to make this distinction is largely technical, conceptually, not really a big deal. All right, let's move on. So now, what was step 2? Step 2 is to show that, all right, NAE-3-SAT is at least as hard as 3-SAT. So let's do that. All right. So first we should talk about what NAE-SAT is. So in NAE-SAT, we have so it's pretty much the same as the regular CMF-SAT, except instead of requiring at least one true literal per clause, we're going to require that each clause has at least one true literal and at least one false literal. In other words, literals are not all equal. That's why it's called NAE-SAT. All right, so is the statement of the problem clear? So it's like the same thing as CNF-SAT. We have these clauses, these kind of little tuples of variables or sets of variables or whatever, and we just want from in each of these to have at least one true literal and one false literal, or to just have them all not be true or all not be false.
So we're going from E3-SAT or 3-SAT?
We're going to show a reduction that works for 3-SAT, but you're going to just be able to plug E3-SAT in just as easily.
Do we have to constrain it to have clauses of size 2 at least, or?
So yeah, so good question. So here, this distinction between E3-SAT and 3-SAT will not be important at all. Here it will be actually most convenient for us to look at NAE E3-SAT. And so we're going to do this reduction not really paying attention to the E3 part, but then we're going to look back and say, hey, if we had started from E3-SAT, this would now be NAE E3-SAT with exactly 3 variables per clause. So we're going to then reduce from NAE 3-SAT to get hardest for 3 coloring. Yes?
Doesn't our construction of the E3-SAT reduction rely on the fact that you can have all 3 of them being false?
Yes, but that's not an NAE-SAT instance.
Right. So if we were just able to plug our reduction from 1 to 2 or 3, then I don't know how that would work.
But it's okay, because forget about the details of your 3-SAT instance. It's a valid 3-SAT instance. We're just going to give you a procedure, takes any 3-SAT instance, converts it to an NAE-SAT instance with the right properties, that it's satisfied, if every clause is a true and a false literal. And it's going to be true that the 3-SAT instance is satisfied in the regular way if and only if the NAE 3-SAT instance is satisfied in the NAE 3-SAT way. And so you'll see in a second. But sure, you may start with an instance of this form, but somehow we're going to give a way of transforming it into another instance that will be okay. Does that make sense? Cool. All right, good questions. Thanks. So we're going to do this in 2 steps. So we're going to go via NAE-4-SAT actually. So we're going to do it like this. And NAE-4-SAT is exactly what you think it is, at most 4 literals per clause. And then we're going to show that this will reduce to NAE 3-SAT. So that's kind of the game plan for this part of things. All right, so we should prove the first step. And again, if we're talking about NP-Completeness, we need to talk about problems being in NP. NAE-3-SAT is clearly in NP. You can go take your possible assignment, go check that every clause has at least 1 true literal, 1 false literal. So it's in NP. So we're not going to think about that anymore. But we're going to worry about this reduction here to show this. So the proof. So we'd like to take 3-SAT instance phi and get an NAE for SAT instance phi prime. And so our reduction is going to be really, really simple. We're going to just make a new variable s. And we're going to add s to each clause. So that's pretty straightforward. So let's, an example of this is you might take the clause x3 or not x5 or not x6, and we'll just convert this to x3 or not x5. Well, actually, sorry, it's NAE, so we'll just write clauses instead like this. x3, not x5, not x6, and s. That's our new NAE 4-SAT clause. So we take a 3-SAT clause, we convert it to an NAE 4-SAT clause of this form. And so note that this can be done in polynomial time. Add a variable each clause. And 2, it's a valid NAE 4-SAT instance. You have 4 variables in each clause. So this is it's giving you the right thing. But of course, we have to prove that it actually works. So let's maybe do this. Up here. Okay, does the reduction itself make sense before we prove that it works? Pretty straightforward. Add a variable each clause. All right, so what do we need to show? We need to show the following claim. And that is that phi is satisfiable if and only if phi prime is satisfiable. Again, in the NAE way, not in the standard SAT way. And we have to, again, prove both directions of this. So in this direction, we're going to say, we assume that phi has a satisfying assignment x. Then we can use the assignment x s equals f for phi prime, and this satisfies phi prime. And the reason is that each clause of phi has at least one true literal, and that's because x satisfies phi. And that's what it means to satisfy phi. It must be the case that there's at least one true literal in each clause. But then we have at least one f as well, namely s. Okay, So, yes?
So like when it says like one true literal, it's like the bottom is not x with this?
Yes.
So it's not like x is true, it's that's like not x is true.
Yes, exactly. And so, yeah, when we're talking about satisfiability of just kind of regular old CNFs, we're talking about a regular old instance of SAT. Yeah, we want one, at least one literal in each clause that evaluates to true. But if it's not x, then you have x equals false, and not x is true. That's exactly right. And so that's the same thing we're saying here. All right. So that's one direction. We got to do the other direction. So here we're going to suppose that phi prime is satisfiable in the not all equal sort of way. And so we're going to suppose that phi prime has a satisfying assignment x s. And so then what we're going to do is we're going to say if this is x and s is false, then we want to we're going to let y equals x. I'll tell you what y is. We'll get to what y is for in a second. And if we have x true, then we're going to let y equal not x, where I use this notation to mean x with each of its variables individually negated. What I claim is that y with s equals false is a satisfying assignment. And why is that? Well, we know that okay, I forgot to make an important point. Sorry about that. Good. So the interesting thing about NAE-SAT, if x satisfies NAE-SAT, then so does not x. So you go through, you negate everything. You had at least one true literal and one false literal in each clause. If you negate, those get flipped. You still have at least one true literal and one false literal in each clause. So we're taking our, this xf or xt. There are so this is like some satisfying assignment for our NAE-SAT instance. But this is also satisfying for the NAE-SAT instance, because all we've done is we've just negated what's there. So here it's exactly the same. Here it's just a negation of this. So both are. This is always going to satisfy the NAE-SAT instance. Is that clear? I should have put that in earlier. Okay. Good. So that means that, so this is y and f. So what that means is that, I want to show you why this is true. So, or why phi is satisfiable. Okay, we know that yf is a satisfying assignment in the NAE-SAT way. And so what this implies is that y must produce at least one true in the, what I'll call the non-S part of the clause. Okay, so this YF satisfies this thing as NAE-SAT. We have this F. So there's this S everywhere. You know, everybody has this fourth guy who's labeled S. It's always false because it's false. So in order to be satisfied as NAE-SAT, Y must produce at least one true variable in the other three variables of the clause. Okay, so this means that Y can't write this morning. Y satisfies phi. Okay. Does that reduction in its proof make sense, despite the fact that I stumbled over it a little bit? Cool. All right, so first step's done. Onward. So now, step 2b, you might say, is following theorem. And that is that NAE-4-SAT reduces to NAE-3-SAT. So once we've shown this, we've shown point 2. All right, so how are we going to do this? So of course we want to take an NAE-4-SAT instance to an NAE-3-SAT instance such that one is satisfied if and only if the other is. And how are we going to do that? So let's consider clause A, B, C, D in my 4-SAT instance. And what I'm going to do is I'm going to turn it into 2 clauses in my 3-SAT instance. So I'll double the number of clauses. And what are those clauses going to be? Well, they're going to look like this. I'm going to add a new variable wi, one new variable for every clause I. So we'll call this clause I. And the 2 clauses we're going to look at are A, B, wi, and not wi, C, D. So we're going to go through our instance. We're going to take every one of our clauses, which have these 4 variables, and we're going to construct our new instance by breaking them into 2 3-variable clauses with this extra variable wi. And that's the reduction. All right. So, of course, it runs in polynomial time. That's pretty easy to see. Yeah, we have this one new variable wi for each clause. Okay. So what's the claim that we need to prove? The claim that we need to prove is that A, B, C, D is not all equal if and only if there exists a wi, a value for wi in true false such that both A, B, wi and not wi, C, D are NAE. So if we prove this, we're done. Because what this is saying is kind of a clause-by-clause way of showing that our 4-SAT instance is satisfiable if and only, or NAE 4-SAT instance is satisfiable if and only if our NAE 3-SAT instance is satisfiable. So the clauses we get, we want this to be satisfiable if and only if these are. Okay, so let's prove that. Let's start with this direction. So we're going to say that these guys are both NAE. And this kind of immediately implies that ABCD is also NAE. And so then you can kind of see this by saying, well, what if this was all equal? What if A equals B equals C equals D? Then what are you going to choose WI to be? So, say that these are maybe both true, and this has to be false, but these are both true, and now this is true and it's not NAE. So the point is that if these are both NAE, then it must be the case that ABCD is also NAE. Yes?
I think intuitively it makes sense to me because there's one true and one false in ABCD.
Huh?
And so WI and not WI will kind of head against both of those.
Yeah.
But don't you have to know which one is the true and which one is the false?
No, because we're kind of talking about existence of a satisfying assignment. So we just have to show that we don't have to say that WI is something or is not something. We just have to show a statement of this form, which is that if there is some satisfying assignment, or if an assignment that we don't know satisfies it, then these are satisfied as well. And I guess that's one part of your question. So we don't exactly care what WI is. And the reason why we can get away with not caring what WI is, and maybe this is the more important point, is that WI only occurs in these two clauses. So you're not going to have any issues with other clauses because it kind of only appears here. And so you can get away with setting WI to be whatever you want. Does that make sense? All right. So good. Now we have to do the other direction. And the way that's going to go is we want to show that if ABCD is not all equal, then some pair is going to be different in these guys. So what's that going to look like? Well, we're going to look at there's going to be kind of two main cases here. And everything else will kind of look like those. So case one is A not equal to B. So if if ABCD is not all equal because A is not equal to B, then what I should do is I should just choose WI to make not WI CD NAE. And the reason I'm allowed to do that is because since A is not equal to B, the first clause is already satisfied regardless. So I have freedom to choose WI how I will. I can choose it to make the second clause NAE. So that's what you can do if A is not equal to B. Case two is A not equal to C, and here I'm going to want to set WI equals C. And when I do this, what's going to happen? A is not equal to C, so then this is satisfied because A is not equal to WI. And then A is not equal to, and then WI is equal to C, so then not WI and C are going to be different as well, and it's satisfied. So those are two cases. And if you kind of sit down and write all cases out, I guess there should be like 6 of them, because there's 6 pairs of variables. You'll see that they all kind of look like this. These are kind of the 2 ways that things can go. And so really the options are, do you have like 2 guys who appear in the same clause not equal, or do you have 2 guys appearing in different clauses not equal? Everything is one of those 2 cases. They all look like this, and that's the proof. Okay, any questions on that? All right. So let's go on to the 3 coloring part. And let's do that here. So yeah, now we're on to step 3. So here's going back to this issue of E3-SAT versus 3-SAT, exactly as you asked. How is that going to play in here? And the minor point we need to make is that we've also shown that E3-SAT reduces to NAE E3-SAT, where this is NAE-SAT with exactly 3 distinct literals with distinct variables per clause. And so in particular, this means that NAE E3-SAT is NP-complete, because we already showed that E3-SAT reduces to SAT. Okay, so that's good. So then NAE-3-SAT is really nice as a starting point for further reductions. Sorry, need the E there. And why is it convenient for reductions? The reason is because there are a lot of problems that have some kind of symmetry. And what I mean by that in the case of NAE-SAT is that, again, we have this thing where, which literals are true and which, like, true and false don't really matter. So if you flip true and false, you still satisfy it. So somehow there's kind of labels, you can kind of switch them arbitrarily, and that's the kind of symmetry I'm talking about. And so NAE-SAT kind of has this property. And so, like, for example, yeah, so there's really no difference between true and false. And this is, not the case for regular 3-SAT. You don't have that same sort of symmetry. And for coloring problems, like 3 coloring, there's really no difference between our colors, which for this lecture will be red and blue and yellow. So you have, a 3 colorable graph, and you kind of color it in a certain way. If you just kind of permute the colors, you still get a valid 3 coloring in the graph. It exhibits a similar sort of symmetry. And so that's why it's going to be convenient for us to use a problem like NAE-3-SAT that has a similar sort of symmetry. And hopefully, this will become clear as we do the reduction. And just more generally, when you do reductions, it's kind of really important what you start with. That can make your life a lot easier or a lot harder. And so here we're kind of being smart and saying, NAE-SAT is a good thing to start with for 3 coloring. This kind of conceptual point makes sense, hopefully, as we discuss it. Yes?
So for concluding that E3-SAT reduces to NAE-3-SAT, it's just you apply NAE-3-SAT restriction and use the same reduction.
So that's not quite what we're doing here. Rather, here we started with 3-SAT and got to NAE-3-SAT. And so instead what you can do is start with E3-SAT and get to NAE-E3-SAT. So we're never really going from NAE-3-SAT to NAE-E3-SAT.
Oh, so you're starting with an E3-SAT.
We're starting with E3-SAT. Yes, starting with E3-SAT, do the exact same reductions. Then you get hardness of NAE-E3-SAT, and now that's what we're going to start with for this 3-coloring reduction. Yes, good. That's a great question. Good thing to clarify. Make sense? All right. Let me know if you have any questions. Good. So now to conclude this first section, we will prove the following theorem. NAE-E3-SAT is going to reduce to 3 coloring. So proof. And in doing this proof, what is our goal? We want to convert NAE-E3-SAT formula phi to a graph, which I'll call G phi, such that phi is NAE satisfiable if and only if G phi is 3 colorable. All right, this is what we're trying to do, our goal. How are we going to do this? Well, we're going to kind of do this in 3 steps, or 2 steps rather. And the idea is similar to this thing we did in this first reduction where we wanted to kind of add this extra variable and kind of always make it false. Similar sort of thing will happen here. All right. So, yeah, we're going to kind of develop this in 2 steps. So one, we're going to first kind of think about how we might encode kind of a true and a false assignment to the variables of our NAE-SAT instance as a coloring. And so how might we do that? So what we're going to do is we're going to start to build our graph. And we'll see how this kind of falls out. Bless you. And we'll start with by adding a vertex, a new vertex. Well, I guess everything's new so far. And we'll call this ground. So we're adding 1 vertex to our graph. Then, for every variable, we're going to add 2 more vertices. 1 for the variable, 1 for its negation. So here, maybe I have vertex for xi, I have a vertex for not xi, I have a vertex for yi, I have a vertex for not yi, I have a vertex for, oh, sorry, this should just be x. Yeah, so a vertex for x, a vertex for not x, a vertex for y, a vertex for not y, a vertex for z, and a vertex for not z. And you can imagine that you can do this for all your variables, but I'll just show for 3 here. And then what do you do? Then we're going to draw these triangles. So we're going to add these 3 edges here, these 3 edges here, these 3 edges here. And we're going to do this for all variables in the same way. And what does this get you? Well, I claim it kind of gets you a way of thinking about true and false assignments as colorings. And in particular, without loss of generality, by this kind of symmetry property, I'm going to assume that ground is colored yellow. And so by doing that, because I have this structure, this guy's yellow, so these, everything, all the, the triangle here, so this is yellow, so these must be red or blue. These must be red or blue. These must be red or blue. And they also must be opposite in color because they're connected by an edge. So if this is red, this is blue. If this is blue, this is red. And so now red and blue correspond to true and false. So if I have, for this graph, which is the only thing I've drawn so far, if I have a valid coloring for this graph, I get a valid assignment of the variables to true and false. I haven't talked about the clauses yet, but this kind of just encodes an assignment of these variables to true or false. Good so far? OK. So the next thing we have to do is we have to encode the NAE constraints in this graph. And the way we're going to do that is we want to, for each clause in our NAE-SAT instance phi, we're going to want to add something that's kind of an example of what's generally called a gadget. And in our case, that's going to be a subgraph that is 3-colorable if and only if the truth assignment induced by that 3-coloring satisfies your clause. For each clause C, we'll say. So for each clause C, we're going to add a gadget. That's some subgraph that's 3-colorable if and only if the truth assignment induced by that 3-coloring satisfies the clause. And when I say the truth assignment induced by the 3-coloring, I'm talking about what I just said, where kind of assume this is yellow, then any valid coloring of this induces some truth assignment. So if we can do this, then we're set. And this will become clear when I show you what it actually is. But this kind of idea makes sense. OK. So what's this going to look like? Let's say that we have clauses x, y, z. And maybe we have another clause, not x, y, not z. And I want to put something here and connect it to x and y and z. And I want to put something here. So like, yeah, what should these gadgets be? And I want to connect it to not x, y, not z. So what should, so the question is like what this is kind of a picture of what we just wrote. So what should this be? And so turns out the answer is straight. Does anyone have an idea of how we can do this? It's quite straightforward. And so all we do is we just make a triangle. And do the same over here. And that's it. So of course, you do this for your whole instance. You've kind of gone through and you've added all these variables for every vertex, connected to the ground in the same way, connected to opposing, opposite literals in the same way, and then for every clause, you're going to add this triangle connected to its corresponding literals. And I claim that that works. To see that, what do I need to show you? I need to show you kind of that it works in both directions. That if I have a valid NAE-SAT assignment, then I get a valid coloring, and vice versa. And so imagine that you didn't have a valid coloring, that there was some triangle here. Sorry, imagine that your NAE-3-SAT instance was not satisfiable. Then you would have the corresponding truth assignment here would mean coloring to the truth assignment would mean that this triangle was connected to 3 vertices of the same color, right? So if NAE is not satisfiable, then some clause has all 3 literals the same. The corresponding triangle is connected to 3 vertices of the same color. And so now there's no way to color that triangle, because we've connected it to 3 vertices of the same color, and the 3 vertices of the triangle must be different colors themselves because it's a triangle. And so there's no way to do that. So let me write this down with an example, and you will see. So say this is blue, and this is blue, and this is blue. Okay, now color this for me. How are you going to do that? Well, I could try red here and yellow here, and now I'm stuck. Because it's NAE, so these are all blue, and this guy's connected to a blue and a yellow and a red, so I have no valid way of coloring it. On the other hand, if this were red, then I'd be all set, because then I could color this guy red, this guy yellow, and this guy blue. And now it's colorable. And so this gadget exactly captures what we want, which is that it's 3 colorable if and only if the truth assignment induced by the 3 coloring satisfies the corresponding NAE clause. And that's the proof. Are any questions about that?
This works because there's each 3 clause. I use 3 comparative literals, one of them, there has to be 1 true and 1 false. So there's at most 2 that are.
Yes, exactly. And for that reason, you can then find a valid coloring of the gadget. And if it weren't the case, then there would be any way you try to color all 3 vertices, you're going to have a problem. Because there's going to be that last vertex, which is adjacent to its 2 neighbors in the triangle, plus the other guy of the same color. And there's no choice. You can choose to color it. All right. Any other questions about this? Okay. I'm a little bit behind, so maybe we'll talk a little bit about independent set. We'll see how far we get. But yeah, that concludes our reduction showing that 3-SAT reduces to 3 coloring. So now, where did I put my notes? Aha, good. Okay, independent set. Independent set is another computational problem, of course. And in it, we have graph G, we have some, natural number K, and the question is, does G contain an independent set of size K? Do you guys remember what an independent set is? So an independent set is a set of vertices such that no pair of vertices in the set has an edge between them. So it's just a set of vertices, no pair of which is connected by an edge in the graph. Okay. Statement of problem clear. Okay. I think we can do this in a couple minutes. So here's the, and this is not a CSP. This is why this is interesting. So we've been talking about CSPs the whole time. Now we're going to actually show that a non-CSP type problem is NP hard. Okay. So the theorem is that E3-SAT reduces to independent set, and here's the proof. And maybe, okay, so what's the goal? So given an E3 SAT instance phi, we want to construct a graph G phi and a number K phi such that phi is satisfiable. Now we're back to 3-SAT. So in the regular way, if and only if G phi has an independent set of size K phi. This is the goal. Make sense? All right. So I have 1 minute, but I think in that minute, I can draw you a picture. And this picture will hopefully convey everything you need to know. So maybe I'll do a really good job and draw it big on this board. So yeah, what does the reduction look like? It's pretty straightforward. So here's how it's going to go. So I'll do it by way of an example in the remaining minute. And so you have x1 or x2 or x3. This is some set instance. And not x1 or not x2 or not x3 and not x1 or x2 or x3. So what I'm going to do is I'm going to draw a triangle for each clause. And so this is x1, x2, x3. This is not x1, not x2, not x3. And this is not x1, x2, and x3. And then all I'm going to do is I'm going to connect vertices corresponding to opposite literals. So x1, not x1, x1, not x1, x2, not x2, x2, not x2, x3, not x3, and x3, not x3. And so you can, of course, imagine doing this for all clauses. And I claim that this works, and class is over.